We'll start our session by writing the data given in this example. Data given. So just a minute. Yes. So here it is, whatever the data given to us. So first of all, we'll write the data given to us. When a 440 by 110 volt single phase transformer, so this transformer's voltage ratio is 440 by 110, so we can write that primary voltage is equal to 440 volt and secondary voltage V2 is equal to 110 volt. It is a single phase transformer operated on no load condition. So this is also important information. It operates at no load condition, right? It draws 6 ampere from the supply means. That means the no load current, which is known as I0, is equal to 6 ampere from the supply means. So many different participants, right, like electrical jigyasa and electrical jigyasa in Hindi also joined the session. Welcome everyone for this session. Uday, Janice, Sonu, Jairaj, Kevin, welcome everyone for this session, right? So we had just started the session, right? Good morning, Parth. So participants are joining in the session. Welcome all the participants, and I would like to tell you all that we has just started the session and we are writing the data given in this numerical. So we have written the data. V1 is equal to 440 volt, V2 is equal to 110 volt, the transformer is operated on no load condition, and I0 is equal to 6 ampere, which is basically the no load current of the transformer. The power factor of 0.25 lagging. So this current is drawn 50 at 0.25 lagging power factor. There are 110 turns in primary winding. So N1 primary winding number of turns is equal to 110. So now we need to go for data to find. What data exactly we need to find in this transformer? First we need to find the iron loss, right? First of all we need to find the iron loss, then magnetizing current. We denote magnetizing current by I mu, and maximum value of flux density in the core, right? So we need to find maximum value of flux density in the core. So flux density is Bm. So this three thing we need to find. So how we will proceed, that is the most important thing. So first of all, let's observe that what we need to find, the iron loss. What next we need to find, the magnetizing current and the flux density. So to understand what exactly we need to find and how we can proceed to solve this example, for that we need to draw the diagram, the vector diagram of transformer. It is always important that you should have clear idea of what you need to find. So this is the flux, right? On vertical axis we will draw the E1, right? Why it is like this, that we have already studied in our previous session. So right now I am not going in deep that why it is 90 degree and all that thing. Here we'll consider that this is the flux 5, it is the E1. Now the no load current is basically this, we call it I0, and this I0 has two components. The first component is horizontal component, is this, and is known as I mu, which is known as magnetizing component, and the another component is this, which is known as IW. The IW current is basically responsible for the iron loss or minor amount of copper loss in primary winding. I mu is completely responsible to magnetize the core. So now we have a clear idea that what exactly we need to find. We need to find first the iron loss, and what is ultimately a power loss is. A power loss is ultimately Vi, right, or I square R or Vi cos phi, right. So in this case, this power loss will be multiplied by voltage, this current, and this power factor. So how we can get the iron loss? So we'll write solution. So how we can get the solution? So the iron loss in this machine or in this transformer, we can write it as, or denoted by Wi, iron loss, is V into IW. So Vi will be the iron loss in this machine. Now do we know this IW? We don't know this IW, right? But to get this IW, we need to use this IO current. Why we need to use this? Because here there will be V1 voltage, and the angle between these two is known as the cos phi. Right now what we'll do, we will take this thing, that angle between these two is given to us as cos phi, which is 0.25. So how we can get IW? IW will be I0 into cos phi, right? IW will be I0 into cos phi. What is I0? The value of I0 is 6 ampere. We have that. What is cos phi? It is 0.25. We have that. So if we place these values, 6 ampere multiplied by 0.25, then by calculating it, 6 multiplied by 0.25 gives us 1.5, right? So the IW is 1.5 ampere. So now from this we can get the iron losses. The terminal voltage V1 on supply side is 440 volt. So let's place these values. Sorry, we'll take the black pen. So V1 is 440 multiplied by 1.5. So 1.5 multiplied by 440 gives us 660, right? So the Wi is equal to 660 watt. Wi will be 660 watt, right? If anybody has any doubt, you can ask me anytime, right? So now let's move ahead. We have got the iron losses, which is 660 watt. Now we need to find I mu. And what is I mu? I mu is the horizontal component of I0. So if you let me rub it. If you draw this dotted line over here, which is same in length as of I mu, then using this diagram you can write that I mu is equal to I0 into sine phi. So I mu is basically I0 into sine phi. Now from where this thing comes, if you don't know, then in short I am describing this thing, that this is our I0, this one is IW, and this one is I mu. This angle is given to us, and that is cos phi, right? That is not cos phi, I'm sorry, that is phi, right? Now if you want to write the cosine angle, then cos phi is equal to the nearby side and the adjacent, so IW by I0. So from this you can write IW is equal to I0 into cos phi. And if you want to write for sin phi is equal to Im divided by I0, sorry, I mu divided by I0. So you can write I mu from here I0 into sin phi. So this is a simple trigonometry mathematics. So from this equation, or from this logic of sin phi angle, we can get I mu is equal to I0 into sin phi. Now the next task we need to find is I mu, which is I0 into sin phi. Do we know the value of sin phi? No, we don't know what is sin phi. But how we can get the sin phi? So the cos phi angle is given to us. Cos phi is 0.25. So phi is equal to cos inverse of 25. So we can write that. Is it possible to have, sorry, it's not, I'll do it in my mobile, right? Just a minute, I'll do it in my mobile and I'll let you know. Let me calculate this sin phi, and then this phi will place so that we can get the sin phi. Let me calculate this thing. Cos inverse and we can get sin phi is equal to 0.986. So now we have the value of sin phi. I0 is equal to 6 ampere. So I0 is 6 ampere, sin phi is 0.986. So we can get I mu 6 into 0.986 gives us 5.916. So we'll take it as 5.92. So 5.92 ampere of magnetizing current will flow. Now we need to find the flux density, right? Maximum flux density. What is the equation of flux density? The equation for flux density, B is equal to phi by A. For maximum flux density is phi m by A. But observe the data given. Here we do not have A, the cross-sectional area. So when we do not have this cross-sectional area, what we can do, we can assume that A is unity, A is equal to 1. And once we assume that our cross-sectional area is unity, we can go for Bm is equal to phi m. Why? Because we are assuming that our cross-sectional area is unity. And why we are assuming our cross-section area is unity? Because it is not given in this numerical, and there is no other way by which we can find the cross-sectional area. So by default we will consider this thing as a unit cross-sectional area, and then we will go for finding Bm is equal to phi m, because A is equal to 1. So now we have the equation induced EMF in transformers primary. E is equal to 4.44 phi m f into n1. So this phi m f into n1, this is primary number of turn, this is the frequency, right? Do we have the frequency? No, we do not have the frequency, and when we do not have the frequency, we are in India and our frequency is always constant, right? So we can calculate it as phi m is equal to E1 divided by 4.44 f and 1. We have some other students who are answering. Sahdev is answering 75.52. So very good, Sahdev. Keep on doing this type of things, right? You find sometimes that there is a lag between I am reading the comment and answering to you, because it's tough, to while calculating the example and monitoring several things like comments and your questions and all that thing. So just ignore this thing, this type of delay in responding to you. It happens here in live sessions. I hope you all forgive me for this. Okay, let's move ahead. E1, that is our primary voltage, that is 440 volt. So it's 440 volt. Now 4.44 f is the frequency, 50 hertz, and n1 is primary number of turn. It is 110. It's given over here, primary number of turn, it's 110. So now this is 110. So phi m is equal to 440 divided by 4.44 divided by 50 divided by 110. So it gives us 0.0180180180180. Wow, what a fantastic number, right? It's good number, right? 0.0180 is the answer. 0.0180 Weber. So this is our maximum flux, and the flux density Bm will be 0.0180 Weber per meter square. So this is our answer. Do not stop here, because in example it is asked to calculate flux density, right? So that's good. Even Sahdev has calculated the answer. I appreciate your efforts, Sahdev. I request all the other students to actively participate and keeps on answering, right? So this is the end of our example number 1. If you have any doubt, you can definitely ask me, right, in comment section. If you do not have any doubt, then we can quickly jump to the example number 2. And here we go. This is our example number 2. So let's begin the example number 2. Data given. A single phase 1100 by 230 volt. So this gives the primary and secondary voltage. V1 is 1100 volt and V2 is equal to 230 volt. Transformer takes power of 600 watt. So P is equal to 600 watt at power factor of 0.8 lagging at no load. Okay, so cos 50 is equal to 0.8 lagging at no load condition. So all the data is given to us at no load condition. Okay, so everything is given at no load condition. What is to be calculated? Calculate the core loss. So we'll write data to find, and what data we need to find? Core loss component. core loss component and magnetizing component. So magnetizing component, that is I mu of no load current. So we need to find the magnetizing component and core loss component. So for that we will quickly draw the diagram, vector diagram. It's our phi, right? Over here we'll draw V1 or E1, whatever we can call it for this example. There are two currents. One is, this is known as I mu, which is magnetizing component, and the another one is this IW, which is iron loss component or core loss component for the primary side. Basically this core loss component, the amount of core loss occurs in the primary side is very small, but for that this component is responsible. So let's draw the vector diagram of I0 from this. So this is our I0. Basically I0 is known as no load current. So I0 is no load current. So what do we need to find? Core loss component. So we need to find IW, and copper loss magnetizing component I mu, right? The data given that cos phi angle between voltage and current, this angle is the angle is not given, but the cos phi is 0.8. So cosine angle between these two, cos phi is 0.8. So if you want to calculate this angle, you can calculate it using this method. Cos phi is equal to 0.8. So phi is equal to cos inverse of 0.8. So now I am leaving this up to you, that how much is the phi angle, please tell me. And from this I will write sin phi directly calculating in my mobile. Sin phi is equal to 0.6. So when cos phi is equal to 0.8, sin phi is 0.6, and you can calculate and tell me, okay, that's good, Sahadev has calculated 36.86, that's good. So now we'll go for the solution. So whatever data given to us, from that we need to find IW. And how we can find IW? IW is basically, let's write for cosine angle, cos phi is basically IW divided by I0. IW divided by I0. And what would be the sin phi? Sin phi is equal to this I mu divided by I0. So I mu divided by I0. So from this we can calculate IW is equal to I0 into cos phi, and I mu is equal to I0 into sin phi. So okay, so other participants also has joined our session. Thank you Gujarati Mijaj for joining the session, and keep learning using this live session. So all the participants, you can also calculate this thing with me. We have the value of I0, right? Do we have the value of I0? No, we do not have the value of I0. Now, is it a trouble for us? Is it a trouble for us? No, it's not a trouble for us. Why? Because the data given to us over here, power P. And which is this power? This power is drawn by the transformer at no load condition. So the power drawn by the transformer at no load condition is known as P is equal to VIW, right? VIW. Now what is IW? IW is I0 into cos 5. So let's replace this thing, V1 I0 into cos 5. Power is given to us, it's 600 watt. V1 is known to us, it's 1100, and cos 5 power factor is 0.8. So from this we can calculate the I0. So who can calculate this thing with me and answer before I can calculate the answer? Please write the answer in comment section if you can calculate it before me, or if you cannot calculate, still you can write the answer in comment section. But your active participation is always important for me, so please actively participate and write the answer. And thanks, several students are appreciating our teaching techniques. Thanks friends. Ashish, thank you. So now it's I0. So where we are, I just forgot. Let's get back to the session. I0 is yes, P divided by V1 and cos 5. So what is P? It's 600 watt. So P is equal to 600 watt. V1 is 1100, and cos 5 0.8. Has anybody calculated this and got the answer? Okay, Sahdev has got the answer, Anish has got the answer, very good. Let me try. 600 divided by 1100 divided by 0.8, it gives us 0.68. So it's 0.68 ampere. But the answer given by students is 20 ampere. Oh my god. What's the difference? It's 0.68, but everybody is getting 20 ampere. How? How come this is true? See, what we are going to calculate. We are going to calculate I0. And what is I0? I0 is equal to P divided by V1 divided by cos 5. So calculator, power is 600 watt, right, divided by 1100 divided by 0.8 power factor, so it's 618. So that's our I0. So please, if you have made any mistake, then please correct it, right? So I0 is 0.68 ampere. So now let's place this 0.68 ampere of I0 into 0.8 will give us IW, and IW is 0.68 multiplied by 0.8 gives us 0.545. So IW is 0.545 ampere. So it's a half of the ampere, and I mu is equal to 0.68 into sine 5, 0.6. So 0.68 multiplied by 0.6 is 0.408. So I mu is equal to 0.408 ampere. So that's it. This is our two component, core loss component and magnetizing component. This is our example number 2. If you have any doubt, you can ask me in comment section. I'll wait for half of the minute and then we'll quickly switch to the session next example, that is example number 3, and that will be little bit trickier than these two examples, so please stay alert because the upcoming example is little bit trickier than the first two examples. Okay, so let's move for the next example. And anytime if you find any question you can ask me, right? So students are replying, no issue, then we can move further. So there we go. This is our third example of the day. So we'll take our green pen and write data to find. So let's go for what data we need to find. The turns ratio of single phase transformer is 10:1. That means N1 by N2 is 10:1. When the primary winding is connected to 1100 volt supply. So the primary winding is connected to 1100 volt supply. That means V1 is equal to 1100. It takes a current of 3 ampere at 0.25 power factor lagging. So I is equal to 3 ampere and cos phi is equal to 0.25 lagging. Find the magnetizing current. Okay, so now we need to find magnetizing current I mu. If now the secondary winding supplies the load of 15 kilowatt. Okay, so from here the next condition is given. If now the secondary is supplying P2, from secondary side the power is supplied is 15 kilowatt. So the secondary winding is supplying 15 kilowatt of load, right? So this is power rating of the load connected to the secondary of that transformer at 0.8 lagging power factor. So cos phi 2 is equal to 0.8 lagging. Find the value of primary current and the power factor of primary side. Okay, so we need to find primary current and cos phi 1 primary power factor. So this is what we need to find. So first let's be clear that what exactly this example is, what it wants to say and what exactly it wants us to find. For that we'll draw the vector diagram first. Here we have the flux 5. We draw the primary voltage V. The data given to us, it takes a current and no condition is given. That means this current and this power factor is of no load condition, when there is no load is connected to the transformer. So we can call this as I0. So this 3 ampere of current will become I0 is equal to 3 ampere. This current has two components. One I mu, that is magnetizing component, and IW is working component or active component. So here we have the two component. Now as the load is connected in secondary, there will be secondary side induced EMF E2, and because the secondary is delivering this 15 kilowatt of load, there will be I2 current flowing from the secondary side, right? So this is I2 current which flows from the secondary side. And finally we need to find value of primary current. So basically the primary current is constructed of the no load current as well as the balancing current flows from the primary to balance the secondary current I2. So how much the balancing current will be? The length is equal to this I2 and the direction is opposite to this I2. So it's like this. So this is I2. So the vector summation of this I2 dash and I0 gives us I1. So let's add this to, this is our I2, right? We'll call it as I2 dash, and the vector summation of these two gives us I1. So what the data we need to find? This black, or we'll just make it red. We need to find this I1, we need to find I mu and primary power factor. So we need to find phi, and from that phi we need to calculate cos phi 1. So these three things we needs to find. So first of all, we'll start with the easiest one, which is I mu, magnetizing current. So let's go for the solution now. Solution. So the primary power factor cos phi is given to us. That means this power factor is when there is no load is connected. That means this angle is given to us 50. This is 50. So this is cos 50. So let's write this cos 50 over here. Cos 50 is equal to 0.25. So from that 50 is cos inverse of 0.25. Calculate this 50 and tell me. I am directly writing, when cos 50 is 0.25, what is sin 50? Is 0.968, right? You just write what is 50 in comment section. So now how we can calculate this I mu? So this I mu is basically sin phi 0 is equal to I mu by I 0. Sin phi 0 is basically I mu by I 0. So I mu is equal to I 0 into sin phi. I 0 is 3 ampere and sin phi is 0.968. So we will get I mu as 0.968 multiplied by 3 gives us 2.904, right? So we get I0 as 2.904 ampere. So this is our I mu. Good. Amit Kumar and Sahadev, they all are trying. That's good. I appreciate your efforts, Amit and Sahadev. So we got the first finding, that is I mu, and now we should move for our next finding, that will be the I1. Now if we want to find I1, we directly cannot find I1. So for that we need to go for a path, right? So to find I1, first we need to find I2 dash, and to find I2 dash, first we need to find I2. So first of all, we'll go and find I2, then I2 dash, and from I2 dash what we'll do? We will vector sum, we'll do the vector sum of I0 and I2, and then we'll finally calculate the I. So now to find I2, what do we require? We have the power. Equation of power is Vi cos phi, right? The equation of power is this much of power load is drawing. So from this we can calculate the I2. So power is given to us, we need to find this. Cos phi is given to us, that is 0.8, but for that we still require the secondary voltage. So first, to find I2, we require the secondary voltage V2. So how to get the secondary voltage? So again, let's observe the data given to us. Yes, we can find it easily because there is one equation. The equation is V1 by V2 is equal to N1 by N2. So N1 by N2, the turns ratio is given to us. V1, this is the turns ratio which is given to us. This is V1, that is also given to us. So we can calculate V2 from this. V2 is basically N2 by N1 multiply by V1. So N2 by N1 is 1 gem 10 and V1 1100. So it directly gives us 110 volt. So the secondary voltage is 110 volt. So now we have V2. Just place the value. I2 is equal to P divided by V2 cos 5. P is 15 kilowatt. So just convert this kilowatt into watt. So it's 15,000 watt. 110 volt, and cos 5 is equal to 0.8. So what will be the answer? 15000 divided by 110 divided by 0.8 gives us 170.45454545. Wow. So it's 170.45 ampere. So we got the secondary current, that is 170.45 ampere. So now we got the I2 current. Now what we need to do, the reflection of I2 will be on the primary side. So this is I2 dash. So what will be the I2 dash exactly? See, whenever the transformer starts working, when it is at no load, it draws only this much of current, right? Understand this thing very clearly because this will be useful in many examples. So whenever transformer is at no load condition, it will draw only I0 no load current. But when transformer is connected to some load, its secondary current starts flowing, and because of its secondary current starts flowing, it draws a little bit more current from the primary side. So that more current is the primary balancing current, or we can call it as balancing current for the secondary current, right? So this I2 dash is basically the balancing current when this secondary has started flowing the I2 current. And how we can get this balancing current? It is very simple. We all know the definition of transformer. Transformer definition is P1 is equal to P2. The power in transformer, the input power of the transformer is equal to the output power of the transformer, and we can write V1 I1 is equal to V2 I2. So here this is I2 dash, the balancing current, right? So how we can get? I2 dash is equal to V2 I2 divided by V1. What is the value of V2? 110. I2 is equal to 170.45, and V1, which is given to us as 1100 volt. So 170.45 multiplied by 110 divided by 1100. So it's 17.045, right? 17.045 ampere. So this has become our I2 dash, right? This is our I2 dash. So now observe over here. I am drawing this vector diagram again, right? Just to have a clear idea. And I am drawing this much only. This is our flux. This is our V1 voltage. This is our I0. I'll write I0 a little later. And this is the I2 dash, it's I0. So now how we can get this I1? To get this I1, let me draw the horizontal and vertical component of I0 first. So the horizontal component of I0, we'll call it as I0H, and vertical component we'll call it as I0V. Now let me draw the horizontal and vertical component of I2 dash with red lines. So it comes up to here and it comes up to here. So the horizontal component is I2H dash and the vertical component is I2V dash. So now if I want to calculate the I1, what I need to do is I need to add this horizontal component and these vertical components. So what I will do, first I will find this total horizontal and total vertical, and then I will add these two. So now what we are doing, we are calculating I1. So first of all we'll go for the horizontal components, right? And that will be I1, this will be the final angle phi, right? This will be the final angle phi. So if we want to go for vertical component, that is cos phi, right? The vertical component will comes with the cos phi. So I1 cos phi 1 will gives us vertical component is equal to I0 cos phi 0 plus I2 dash cos phi 2 dash, right? I0 is 3 ampere, it's 3 ampere, and cos phi 0 it's initially given to us as multiply by 0.25. I2 dash we have just calculated, that is 17.045. let's take it as 17.4, and I cos phi 2 dash it's 0.8, it's given over here, right? So it's 0.8. So now calculate this thing. 17.04 multiplied by 0.8 gives us 13.63, and 3 multiplied by 0.25 gives us 0.75. So 13.63 plus 0.75 gives us 14.38. So this is our I1 cos phi 0. So we have got this. Now we'll go for I1 sin phi, right? It's not cos phi 0, it's cos phi 1, sorry, it's cos phi 1, and over here it's sin phi 1. Okay, so good, Jairaj, Sahadev, Parth, they all are calculating. That's very good, Amit. Very good, very good. I appreciate your efforts. Very good. You all are calculating it with me. I like it. I1 sin phi 1 is equal to I0 sin phi 0 plus I2 dash sin phi 2 dash. I0 is 3 ampere when cos phi is 0.25, sin phi is 0.968, right? Yes, it is 0.968. I2 dash is 17.04 multiplied by sine 5 2. When cos 5 is 0.8, sine 5 2 is 0.6. That you need to remember, it's always be the same. So now let me calculate this thing. 3 into 0.9 968 gives us 2.904. 0.904 plus now it's 17.04 multiplied by 0.6, it's 10.224. so 10.224, when we add these two plus 2.904 gives us 13.128. so 13.13 we'll consider this, 13.13. So now we have the cos 5 component and we have the sin 5 component. That's very good, Jairaj and Janish. I appreciate your efforts. Keep calculating with me. So we have got this I1 cos phi 1 and I1 sin phi 1. Now we'll go on next page. Let me add a page, right? So now we'll go for the I1. And what will be the I1? I1 will be the under root of I1 cos phi 1 square plus I1 sin phi 1 square. So what will be the value of I1 cos phi 1? That will be 14.38 square plus I1 sin phi 1 is 13.13 square. So 13.13 into 13.13 gives us 172.396 14.38 multiplied by 14.38 gives us 206.78 206.78 under root of this plus 172.396, so 379.18, and under root of this gives us 19.47. So 19.47 ampere of I1 current will flow. So now we have got the I1, our second finding, and the third thing which we need to find, right? The third thing which we need to find is cos phi 0. So this angle phi, and from that cos phi 1 we need to find. It's just a slip of tongue, please forgive me. How we can find that thing? We'll take a ratio that I1 cos phi 1 divided by I1, because now we know I1 and we previously know I1 cos phi 1. I1 cos phi 1 is 14.38. So what we'll do, 14.38 divided by 19.47 gives us cos phi 1 is equal to, good job Sahdev, Kamlesh and Anish, good job, good calculation. 14.38 divided by 19.47 gives us 0.7385. So we'll take it as 0.74. So 0.74 will be the cos phi 1, right? So this is our example number 3. So if you want to observe our example number 3, here it is for you. Just observe this example. This one is a little trickier, not tough one. And the another section of this is at here. So this is how you can calculate all these three quantities, right? And now this is the end of our session. If any student or any participant has any question, you can definitely ask your question in comment section. And if you do not have any query or doubt, then we are going to end our session.